Okay, part 3. So we just worked out the individual conserved charges corresponding to rotations. And now we're going to do the same thing for boosts. So if we go back to our expression for our conserved charge here, and we use our... So remember, we expanded this expression into this sum here, and we said this term corresponded to the rotations, and these two terms corresponded to boosts. So we're going to replace our omega this with two terms, basically just these two terms, kind of. So the expression we get when we do that is this. So our QB will be this expression. And so this is actually, it's easier to see how this splits into three terms. So remember this, we should have one charge for each boost. So we have the sum over k, so we can just immediately identify that the conserved charge for a boost in the, we'll say, kth direction is this. So again, this expression is exactly the same as this expression. The difference is that here we're summing over k, and here k is we're not summing over k. K is just either 1, 2, or 3. And so this QB is the sum of over k of this. So, but if we know that if we have a boost along the kth direction, we know what omega looks like. We know what omega k0 and omega 0 k are. They will just be 1. If you remember from the previous problem. So we can just replace both of these with 1, and our charges will reduce to this expression. And then he has both of these indices raised. So I will, so just remember, when we have our 4 vectors, the difference between the contravariant and covariant components are, so that the time components are the same, but the spatial components pick up a minus sign. So if I want to raise, this k up, I will pick up a minus sign because k is one of the spatial components. And then raising this 0 up, I won't get a minus sign because it's the time component. So I get this expression, just what he has, only, well, he uses I instead of k, but whatever. The charge corresponding to the kth boost is given by, or corresponding to a boost in the k direction is given by this. And then finally, the last part of the problem involves our, so if we take our charge and we qk and we take the time derivative of it, we will get this, which you can verify if you take the time derivative of this. We'll just get this expression using the product rule on each term. And so the first term, so x0 dot, so x0 is t. So taking the time derivative of it, we'll just give a 1. So we'll just be left with t0k. And then I've just written, so again, x0 is t, so I've just written that here. And that's still there. And xk will either be x, y, or z, and so taking the time derivative of that will give 0. So this term goes away, and then this term is still here. And then I can, so we'll assume that our conserved charge is conserved. So anyway, so in other words, we're going to assume that q dot is equal to 0. So if I do that, I have this expression equals 0. And then I'll rearrange, I'll move this term over to the right. So I'll have this, this term is equal to these two terms. And I've moved the time derivatives outside of the integrals, because the integrals are up in space, so I can exchange those. So I end up with this expression. But this expression, so this is just, the integral of t0k, well, that's just the conserved charge associated with spatial translations. So this is the momentum of the field. So this is a constant. And here we have just the derivative of the momentum of the field, but we know it's constant, so this is 0. So we end up with the equation d dt of this is equal to constant, which is what we were supposed to do. And then supposedly the physical meaning of this equation is that the center of energy in the field, like I guess like the center of mass, but the center of energy, this is kind of like the center of energy, moves with a constant speed given by the momentum. It's something like that. I don't know. You can read more if you want, but the important thing for me here is just getting to the expression. So finally, I'm done with this problem. Thank God. It took me a while. A lot of pain. Just look at all this shit. Yeah.